In order to determine the speed v of transverse wave in a stretched wire using resonance, you are provided a sonometer setup as shown in the figure. You are also provided with a set of tuning forks. Part A. In this experiment, the fundamental mode of resonance of the wire is used. What is the reason for this? We know that there is a maximum energy for the fundamental frequency. Therefore, we can identify clearly the fundamental frequency, oscillation for the fundamental frequency. Therefore, we can write there is a maximum energy, or we can write there is a maximum amplitude. We know that for a mechanical wave, there is a maximum amplitude for the maximum energy. So we can write there is a maximum loudness. The best reason is there is a maximum energy. Part B. Draw the wave pattern from the formed between bridges P and Q on the following figure 2 for fundamental mode of vibration of wire. Indicate on the same diagram by drawing an arrow the best position where the paper rider has to be placed and mark it as X. We have to draw the fundamental waveform. It is like this. We have to mark the best place to place the paper rider. It is the midpoint of the wire. And then part C. 1. The distance between the bridges in part B above is L. They have given that this distance is L. And frequency of the tuning fork is F. Write down an expression for the speed V of the transverse wave in the sonometer wire in terms of L and F. We have to consider the length to get the wavelength of the wave. We know that we are considering there are two full loops for a full wave. We are considering this is the full wave. And we know that this is the half of full wave. Therefore, we can write lambda divided by 2. We can remember it. There is only one loop for a half of wavelength. One loop equals half of wavelength. It is equal to length. Then we can subject lambda to L. Then we can use the equation V equals F lambda. V equals F. We can substitute lambda by using L, 2L. Lambda value is 2L. Now we have to write down an expression for the speed V of transverse wave. Then we have to subject V and we can get this is the answer for part 1. We have to write a relationship for V. Then part 2, rearrange the expression in part C, one about to determine the wave speed by drawing a straight line graph using the set of tuning forks with known frequencies, so that dimensions of gradient to be LT minus 1. I will consider dimensions of gradient after getting the equation. We have to select dependent and independent variables. In drawing a graph, the dependent variable is the physical quantity we are changing, and the independent variable is the physical quantity we are measuring. Now we are changing frequency, and this is the independent variable. We have to measure L. It is the dependent variable. We are selecting X values by using tuning fork, and we have to measure corresponding L value. Therefore, independent variable is F, dependent variable is L. We have to subject dependent variable because of we have to get dependent variable to the y-axis and independent variable to the x-axis. Then we can subject L value. I will try to get correct dimension even in the question. We have to subject L value. Then part 2. I will subject L. V divided by 2F. Then we have to get F for the x-axis, but it is in denominator. Therefore, we can get 1 over F for the denominator. It is in y equals mx form. Now we can consider the gradient. We know that V is a velocity. Dimensions of velocity Lt minus 1. Lt minus 1. 2 is a constant. There is no dimension. Therefore, dimensions of gradient is Lt minus 1. Then it is the correct equation, rearranged equation for the part 2. Then part 3. State the independent and dependent variable of the graph mentioned in C2 above. Part 3. Independent variable is the physical quantity we have considered to x-axis. It is 1 over F. Independent variable is 1 over F. Therefore, we have to write independent variable 1 over F. Dependent variable is the physical quantity we have considered to y-axis. It is L. Independent variable 1 over F. Dependent variable L. Then part 4. Coordinates of 2 points selected to determine the gradient of the above graph are 0.002 22 and 0.004 42. Here L is measured in centimeters and F is in hertz. Find the value of wave speed V in meters per second. Now we can consider the rearranged equation. This one. Gradient is V over 2. Then we can write for part 4, gradient V over 2. Then getting gradient, we have to consider difference of y and difference of x. Y values 22 and 42. We can get the difference 42 minus 22. Y axis in centimeters. It is L length. We have to convert it to meters. Multiply by 10 to the power minus 2. Difference of x 0.04004 minus 0.002. It is in hertz. Hertz is the SI unit of frequency. Therefore, we can get without any change difference of x. V divided by 2. Now we have to find the value by simplifying. Value of V. 2 minus 2 0. 4 minus 2 2. multiply by 10 to the power minus 2 divide by 4 minus 2, 2. We can write it multiply by 10 to the power minus 3 equals V over 2. Then I will cancel out this 2 and 2. 10 to the power minus 3 and 10 to the power minus 2. Then 10 to the power minus 1, we can bring 10 to the power minus 1 to the numerator as 10 to the power 1. Then 200 meters per second is the velocity of sound. Then part D. Considering the length of the prongs of tuning fork, which tuning fork is the best for taking the first measurement? Give reasons for your answer. We know that when increase in frequency, we can get logically by using this equation. When increase in frequency, resonance length is decreasing, but we can increase resonance length continuously for the set of tuning forks if we are using frequency from maximum frequency to minimum frequency, because of when frequency is decreasing, resonance length is increasing. Therefore, we have to use the tuning fork with maximum frequency first. But it is not the answer. We have to consider the length of prongs. Then we have to know when length of the prongs of tuning fork is decreasing. It means the small tuning fork is providing the maximum frequency. We have to start the practical from maximum frequency, because of if we are decreasing frequency, we can increase length. Therefore, we can continue practical without bring it again to L equals 0 position. But when writing the answer, we have to write the answer with length of prongs. Therefore, for part D, we have to write tuning fork. We have to use smaller tuning fork. Smaller tuning fork. Then we can write the reason. The highest frequency could be obtained for the small tuning fork. That's all for the answer. But for your knowledge, we can write like this. When frequency decreasing, resonance length is increasing. This is resonance length. Resonance length means length of the wire, not length of the tuning fork. And we can get length of the tuning fork is increasing when frequency of tuning fork is decreasing. It is length of tuning fork. We have to write only this for the answer. Then part D, vibrating directions of two prongs of tuning fork at a given moment is indicated by arrowheads in figure 3. Indicate the vibration direction of particles of stem S of tuning fork at the same moment by drawing an arrowhead appropriately on the same figure. Now we have to remember the vibration of tuning fork. When considering vibration of tuning fork, we can see the vibration in prongs should be in this direction. Then moving A to the right hand direction is A, B. B to the left hand direction. In this part, we can see a transverse wave, transverse vibration. But for the S part, it means stem. For the stem, we can see the longitude vibration. Therefore, vibration should be in this direction or this direction. We can draw any answer to this direction or this direction. You have to remember that for the prongs we can see transverse oscillations, and for the stem we can see longitude oscillations. In part F, masses 1 kilogram, 2 kilogram are 3 and 3 kilograms can be used to stretch the sonometer wire. What is the most suitable mass to be used in this experiment? Give reasons for your selection. Most suitable value is 2 kilogram or 3 kilogram. 2 kilogram or 3 kilogram. Because of, we know that V equals S lambda. We can write velocity of wave in string T over M, tension over linear density, length per unit length, sorry, mass per unit length. If we can substitute lambda as L, and we can consider tension and length of the resonance length of the wire. When tension increases, resonance length also increases. Therefore, we can write the answer. We can get maximum resonance length for maximum tension. Then answer for the part F, most suitable mass 3 kilograms. Because of we can get maximum resonance length for the maximum tension. We can get maximum resonance for the maximum tension. Then part G, if the wire is resonate with frequency F, write down an expression for the amplitude of the wire in terms of F and G. When paper rider just jump off. You have to remember the simple harmonic motion. For a simple harmonic motion, we know that if a stage is vibrating in this direction and if a paper rider is on it, the paper rider just jumps off at this pace because of when moving stage to the downward direction, there is a maximum acceleration for the maximum height, and this acceleration should be greater than G. Should be greater than G. When getting just jump off condition, A should be greater than or equal G, and we can write A means acceleration of simple harmonic motion. We can write acceleration of simple harmonic motion minus omega squared x over y. Now I will consider that as y because of it is a simple harmonic motion in y axis. Now we can get, we know that T frequency equals 1 over period. Period is 2 pi over omega. Now we can consider these two parts and we can get omega value by using frequency. Omega is 2 pi s. Now we can substitute omega to this equation. Then acceleration is minus 2 pi s squared. I will get it as 4 pi squared s squared. Why? Now this acceleration should be greater than or equal g. When simplifying, I will not consider the minus mark because of minus means direction for the simple harmonic motion. Now in question, we have to write expression for the amplitude. At this phase, it means the stage is at the position with maximum displacement. Therefore, we can substitute y as amplitude. Then we can subject amplitude g divided by 4 pi squared s squared. It is the minimum amplitude required to jump off the tuning fork. If the amplitude is greater than this value, the maximum acceleration of the stage, it means wire, is greater than g. If maximum acceleration is greater than g, it should jump off from the wire. Taper rider should jump off from the wire. Then part H, write down a possible error that could be happen when determining the resonance length Ln. Action that you would take to minimize it. We can consider the error. The error is paper rider jumps off within a range of length of the wire. We can't identify clearly the jumps off length. Then action to minimize the error. We have to repeat experiment again and we can get some readings. Repeat the measurement for resonance length.